In fact, section 3 is just about rotational dynamics, which is, remember, we said that in rotational motion, we need a torque to start the rotation. In translational motion, remember, we said that we need a force to start the rotation. What you studied about the force in the 11th grade, similar thing will be studied in here. In this section, we are going to study rotational motion, but very similar way to the translational motion you studied in the 11th grade. So let's remember them. Always I will compare, because I will make a informing about translational motion. I hope you remember it. And then I will make this, what is the similar thing in rotational motion? Linear displacement, remember, delta x. So we studied in the 11th grade as a translational motion. In rotational motion, corresponding quantity was angular displacement, delta theta. So next one, we studied linear speed or linear velocity in translational motion. So in rotational motion, we have angular speed, angular velocity. So omega. Then you studied in the translational motion 11th grade linear acceleration A as a vector quantity, and now rotational motion we studied angular acceleration alpha. So, and we know that translational motion starts with a net force acting on an object. If you don't produce a net force, you cannot start object's motion. And of course, if there's a net force acting on that object will accelerate, you are going to start angular acceleration, linear acceleration if a net force acts on it. In rotational motion, how does rotation start? We know it's the net torque. If there's a net torque acting on an object, remember we studied that if this net torque is counterclockwise direction, so if the net torque is positive, so rotation starts in counterclockwise. If net torque is negative, rotation starts in clockwise direction. So we learned that. And one more thing, now we have similar things. In translational motion, we have mass, amount of matter. How many molecules exist in a substance? This is what mass. You are going to count the molecules, you will multiply all this number of molecules with the mass of one molecule, you will calculate the total mass of the object, which is the amount of matter. So in rotational motion, we have also a similar thing, but this is not the best. This is a bit different, okay? That thing is called moment of inertia. Now, normal moment of inertia is input in the textbook, in the whole physics book, in section 2, but it is not about section 2, mostly about section 3. That's why I always postpone this explanation of moment inertia from section 2 to section 3, because completely about section 3 is moment of inertia. So I will ask a question like this: how does mass of an object affect the motion? If I ask this question to you, what kind of answer will you give me? How does mass of an object affect the motion of that object? How? Greater mass, harder to start the motion, or greater mass, harder to stop the motion. So this is just about that. Mass affects the motion of an object. So same thing in rotational motion also exists. So what if I ask you what affects the rotation of an object? What makes rotation of an object harder or rotation of an object easier? Is, if I ask a question like this, answer is going to be moment of inertia. Moment of inertia makes an object's rotation harder or makes an object's rotation easier. So moment of inertia symbol is I. I will explain in details, but get this one. What we have mass, what mass does in translational motion, which means greater mass, harder to start motion, or greater mass, harder to stop the motion, same thing is done by moment of inertia in rotational motion. Greater moment of inertia will be harder to start rotation, or greater moment inertia means harder to stop the rotation. Now I will explain in detail. So then, moment of inertia in inertia. And when I say the inertia, it's about translational motion. It's indicating to you mass. So what is mass or inertia? It is the resistance of an object to accelerate linearly, because the translational motion is about linear motion if we're on a straight line path. So the resistance of an object to accelerate is called inertia or mass. Same thing in rotational motion is defined like this. resistance of an object to accelerate rotationally. So it's called moment of inertia. Yeah, if an object does not want to start rotation, if an object does not want to stop rotation, so that measures moment of inertia of this object. Remember, it is harder to start the motion of a truck than automobile because truck has a greater inertia, greater mass. So it is hard to start or stop motion of a truck than automobile because truck has a greater inertia, truck has a greater mass. So same thing happens in rotational motion like this. It is harder to start or stop rotation of an object if the object has a greater moment of inertia. Greater moment of inertia. Harder to start rotation or greater moment of inertia. Harder to stop the rotation. So inertia is proportional to mass. In fact, mass defined in the 11th grade as a measure of inertia. Maybe you remember it. Measure of inertia is called mass. But moment of inertia of an object is also proportional to its mass. Yeah, if you have two disks in the same size, but one disk is greater in mass than the other one, so which one will be harder to start rotation? Of course, the one which has a greater mass. Yes, moment of inertia is proportional to the mass. If mass increases, moment of inertia increases. But this is not all. Moment of inertia also depends on some other things. Now I am going to tell you to make an experiment. In fact, I did in this summer course, I will do the same thing again. I want to use your pen. Now everybody has a pen. Now I will open my camera and show you how to apply this experiment. So this is the pen. You see me now?
Yes, teacher, we do.
Okay, now I want you to hold your pen like this and try to rotate your pen from the middle like this, as I did. So now I want you to rotate your pen from the middle first like this. And after that, pull your finger to the end and try to rotate your pen, okay? Like this. So, and compare them. This one is easier to rotate, or rotating the pen from the center of mass is easier. Which one is easier? And then tell me, which one is easier?
Rotating it from the center.
From center is easier. But in fact, I didn't change the mass. What did I do in here? I only changed axis of rotation. So second thing, moment of inertia changes is axis of rotation. Yani moment of inertia on an object changes according to the point object starts to rotate. So first one is absolutely mass. I have one pen. Rotating one pen is easier than rotating two pens. Well, because mass increases. So in this case, if mass increases, so that moment of inertia increases. It is absolute. Keep in your mind. So wherever you add, when you add mass to a system, moment of inertia increases. There is no way. Okay? First one is this. You are going to remind this. Yes, if there is an increase in the mass. If you add mass to a system, moment of inertia increases. Second one is, if you change axis of rotation, as I did in here, first I took the axis of rotation to just the middle, which is the center. This is easier, but when I pull my finger to the end, if try to rotate this pen, yes, it is harder, which tells you that moment of inertia changed. Second one is, as I said, moment of inertia on object changes with where the axis of rotation chosen. Second thing is this. This is a ministry exam question by the time, and then they ask which of the following factors change the moment of inertia of an object. One of them is the mass. Second one is where the axis of rotation chosen. There is one more thing we will learn later in the next slide. Three things can change the moment of inertia, or moment of inertia depends on three things. This sentence is also explained in an alternative way as that sentence. If the distribution of mass of an object is made closer to the axis of rotation, moment of inertia becomes smaller. Or if you make distribution of mass farther from axis of rotation, moment of inertia increases. What does distribution of mass mean? Now I will try to explain that. First, get what does it mean. Now, for identical masses, whose each part has a mass m, okay? If you locate them closer to each other like this, and And if you rotate these masses, assume that you attach them each other, and you start rotating them about this point. And in the second one, you made these masses again, but a little farther the distance between them. So second one, this one is said that distribution of mass is farther from axis of rotation, because in the first one, each mass is closer compared to the second one to the axis of rotation. Yani making distribution of mass farther from axis of rotation means that you are going to expand the mass according to the axis of rotation. Right now, when I hold my pen like this from the center, so this point is, say that at 5 centimeters to the axis of rotation, maximum distance from axis of rotation is 5 centimeters, and that is also 5 centimeters, okay? But if I made it like this, what is distance between this point to axis of rotation, end of the pen to axis of rotation? It becomes
10 centimeters. It becomes bigger.
Yes, this means that distribution of mass becomes farther from axis of rotation. If you make the mass distributed away, I mean farther from axis of rotation, so it becomes harder to rotate an object. This is what distribution of mass means. You are changing distribution of mass by changing the axis of rotation.
Yes, you're right.
Yeah,
thank you.
This is what two sentences are saying the same thing by two different ways, because this sentence also written in your book. That's why better to know it. Okay, now I will continue with definition of moment of inertia. So this is the definition of moment inertia in your book. So moment of inertia is a measure. It's a measurement of an object's resistance to a change in its rotational motion. You know, object does not want to. It wants to keep its state in rotational motion. If it is rotating with constant speed, it wants to continue with constant speed. If it is at rest, it wants to rotate, stay at rest, but in rotational mode. So very similar to inertia, but only definition changes to in rotational motion, not translational motion. Moment of inertia is a measure of object's resistance to change, to change its rotational motion about some axis. And moment of inertia symbol is capital I, and it is rotational analog of mass. What does it mean? I explained. What mass does in translational motion, same thing is done by moment of inertia in rotational motion. Same factor. They have similar effects. So mass, what mass has effect on the translational motion? Moment of inertia has exactly the same effect in rotational motion. Its unit is kilogram times meter squared. Why is it like this? You will learn in the next slide why kilogram times meter squared. So then, if the mass of the object is, if the farther the mass of the object from axis of rotation, yeah, if you make distribution of mass farther from the axis of rotation, so it becomes more difficult to rotate the object, which means moment of inertia becomes greater. So, or if the moment of inertia gets greater, which means it is more difficult to rotate an object. Yani greater moment of inertia, it is more difficult to rotate an object. Smaller moment of inertia, it is easier to rotate an object. Okay, two things I explained. Moment of inertia depends on mass. Second one is axis of rotation, where you choose the axis of rotation. This is second thing. There is one more thing moment of inertia depends on. It is the shape of the object. Shape of the object. Shape also affects the moment of inertia. As the shape of the object changes, we will see that moment of inertia also changes. These are the equations of moment of inertia. We can calculate the moment of inertia on an object by these equations. One of them is mr squared, the other one is 2 over 3 mr squared, 2 over 5 mr squared, 1 over 3 ml squared, 1 over 12 ml squared. What do they mean? I will explain one by one. But moment of inertia for specific shapes have an equation. We will use these equations in the problems. First one, point mass about an axis. Point mass about an axis. What does this mean? If you spin an object, move an object on a circular path like this, As you see, this object is moving in a circular path like this. Yani, if an object is in circular motion, remember we treat this object as a point mass. Do you remember that? Translational motion?
Yes.
Yes, if an object moves a circular path in translational motion, and we should treat this object as a point mass. Point mass about an axis means that this is the axis of rotation, his hand, axis of rotation. And this mass is M is moving, mass of the object, say M, is moving on a circle whose radius is R. Moment of inertia of this object can be calculated by equation mr squared. Mass of the object, mass of the ball, multiplied by square of the radius. For example, assume that this mass is 500 grams, and the radius of the circle is 1 meters. Calculate moment of inertia of this ball about center of the circle. Calculate it. I is equal to mr squared. Very easy. M is, you should convert 50 gram to kilogram, 0.5. R is 1 square of 1. It becomes 0.5. So 0.5 kilogram times meter squared is the moment of inertia of this ball about center of the circle. So point mass about an axis means that. And we will use this in solution of the sum of the problems. Why moment of inertia's unit is kilogram times meter squared? Because mass mr squared, m is kilograms, r is meter, but squared. So as you see, moment of inertia's unit is what? Kilogram times meter squared. Second one is tin hoop about symmetry axis. Tin hoop about symmetry axis is this. By the time, what does symmetry axis mean? Let me say you are going to pass a line through the center of mass. This is the center of mass, also geometric center. A line that passes through this geometric center is known as symmetry axis. Symmetry axis. Yani the line which passes through the geometric center, also center of mass for the object, is known as symmetry axis. So you are going to rotate this hoop about this symmetry axis just like this. Now I will show you with the camera. This is what I am talking about. This is, in fact, ring, a kind of ring. I'm a large ring. It's called hoop, tin hoop. About symmetry axis means you are going to rotate it like this. So this is the symmetry axis. This pan is now in the symmetry axis. This hoop is rotating about this pan. So this is what we are talking about. Tin hoop about symmetry axis, like steering wheel on an automobile. You are spinning, rotating like this. This spinning wheel like this. So this is tin hoop about symmetry axis. I think everybody can see that. So moment of inertia of this tin hoop about symmetry axis is also mr squared. Yani these two objects, point mass about an axis and tin hoop about symmetry axis, has a moment of inertia mr squared. Best example for tin hoop about symmetry axis, and in the book you are going to meet, is a bicycle tire. You see that this is the tire. So this tire can be approximated as a tin hoop about rotating about symmetry axis. This is symmetry axis. Or another small one, also a tire rotating about symmetry axis. Moment of inertia of this tin hoop about symmetry axis is again mr squared. M is the mass of the bicycle tire. I mean the R is the radius of the bicycle tire. So you can calculate moment of inertia of this bicycle tire about its symmetry axis. Second one is that. Second one is a spherical shell, or another name, hollow sphere. Hollow sphere is like a basketball. Inside is empty, hollow sphere or spherical shell. It's spinning or rotating about diameter, because this is the axis of rotation. About this axis, it is spinning or rotating. So this is known as that it's a spherical shell or a hollow sphere about diameter. Its moment of inertia equation is Again, mr squared, but in here there is a rational number. We add 2/3. 2/3 mr squared is the equation for calculating the moment of inertia of a basketball. Yeah, basketball is the question if we are going to meet in this section. It's a good example as well. And next column contains three objects, three shapes: disc, cylinder, and tin hoop about diameter. All these three have the same equation, moment of inertia equation, 1/2 mr squared. This is a good example. I have a disc, but in the book, this is going to be the example for the disc. So like a CD, this is the disc. As you see, it's spinning about symmetric axis. This is the center of mass, also geometric center. So when the line passes about this center, and if you spin about this axis, so this is a disc about symmetric axis. Its moment of inertia is 1/2 mr squared, 1/2 mr squared. Also cylinder. Cylinder is, if you put so many discs side by side, you get a cylinder. That's why their moment inertia equations are same, 1/2 mr squared. Yeah, and cylinder is made up of maybe several discs put side by side, and shape becomes a cylinder. So cylinder and disc have the same moment of inertia, 1/2 mr squared. But last one, tin hoop about diameter is this. Again, this is tin hoop. First one was tin hoop rotating about the symmetric axis like a steering wheel. It was like this. But tin hoop about diameter is this. You are going to rotate it about diameter like that. So this is a line which passes through the diameter like this. Can you see that? This is the line passes through the diameter. If I spin this tin hoop about diameter like that, like this, so tin hoop about diameter. So its moment of inertia 1/2 mr squared as well. So tin hoop can be rotated two ways. One of them, I can rotate it about symmetric axis like a steering wheel of an automobile. Second one is I can rotate it about diameter, just I did in here. Second one is this, tin hoop about diameter. But one of them is the moment of inertia mr squared. Yeah, this is a moment of inertia mr squared, which means rotating that tin hoop like this is harder, but rotating a tin hoop like this is easier because its moment of inertia is 1/2 mr squared. About tin hoop about diameter, we don't have a problem, but better to keep this in your mind. So tin hoop about diameter is rotating a hoop, a ring, like this about a line that passes through the diameter. You are going to spin it like that. But tin hoop about symmetric axis, you are going to rotate tin hoop like a steering wheel on an automobile. Next column is solid sphere about diameter. It is bowling ball, best example, because there will be many problems in this section, which is going to be most about the bowling ball or solid ball. They will say like the solid ball, solid sphere about diameter. This billiard ball is also a good example as well. I don't have a bowling ball in laboratory, but I have this billiard ball. So it is also solid sphere about diameter, good example for that. So moment of inertia of solid sphere about diameter is 2/5 mr squared. 2/5 mr squared. And the last two examples is about rod. Rod like your pen. It's a rod. So length is L. From my finger to the other finger is that length is L, represented by length of the rod. And mass of this pen is M. So if you rotate this pen about one end, just like this, in the experiment I tell you to do, just like this. Moment of inertia is 1/3 ml squared. Yani 1/3 multiplied by mass of this pen multiplied by square of the length of the pen. But if I rotate this tin rod about perpendicular axis to the center. Yani there is a line passing to the center. I am going to hold it so that my finger will, X rotation will pass through the center of the pen. So if you rotate it like this, so moment of inertia becomes smaller. That's why from the easier. 1/12 ml squared. So 4 times easier. Rotating a pen from its center is 4 times easier rotating a pen about its end. So one of them is 1/3 ml squared. The other one is 1/12 ml squared. So in the book only we have mostly problems about point mass about an axis, tube about symmetry axis, spherical shell, discs or cylinder, and solid sphere. Yani many problems in your book will be about these 3, 4, and 5 shapes. About thin rod about perpendicular axis through the end, or thin rod about perpendicular axis to the center, or tube about diameter. We don't have questions, we don't have problems, but better to keep these equations in your mind. So this is all about the moment of inertia.